Welcome to the Explainer. You ever wonder how a site like Amazon or Netflix can handle millions of people all at the same time without even a hiccup? Well, today we're going to pull back the curtain on system design and show you the step-by-step blueprint that powers the biggest websites on the planet, making them super robust, scalable, and incredibly fast. It really does seem like an impossible task, right? But look, it's not magic. It's actually a series of really brilliant solutions to some very big problems. And in this explainer, we're going to build one of these systems from the ground up, piece by piece. So let's start with the very first step of any internet journey. All right, so let's start at the very, very beginning. At its core, the internet is pretty simple. It's just you, the client, on your phone or laptop, connecting to a server somewhere out there in the world. But when you type in a website address, how in the world does your browser find that one right server out of the billions that exist? See, to find anything online, your computer needs a specific numerical IP address. But, can you imagine trying to remember a long string of numbers for every single site you visit? It'd be impossible. And that's exactly why the internet has its own universal phone book. So when you type Amazon.com, the very first thing your browser does is go to a DNS server. It's a super simple lookup. The DNS finds the matching IP address and sends it right back. And just like that, boom, your browser knows exactly which server to talk to. This is that invisible but absolutely crucial first step of every single web request you make. Now, think of a university website on results day. Everyone hits refresh at the exact same moment and boom, crash. See, every server has a limited amount of physical stuff, processing power and memory. When those resources run out, the server just goes down. And this brings us to a really crucial point. For any popular service, a single server is never going to be enough. So to solve this whole overwhelmed server problem, engineers basically have two main choices. You can either make your one server way more powerful, or you can just add more servers to your fleet. Think of vertical scaling like this. You're replacing your regular delivery truck with a massive semi-truck. It's simpler, sure, but eventually you're going to hit the biggest truck size possible. And here's the real catch. Every time you upgrade, you have to take the whole operation offline. That's downtime, a big problem. Horizontal scaling, on the other hand, is like just adding more identical trucks to your fleet. It's a bit more complex to manage, yeah, but you can add or remove trucks whenever you need to without ever stopping the service. Think about it. For a company like Amazon, just 1 minute of downtime during a big sale could literally cost millions of dollars. So that absolute need for zero downtime makes horizontal scaling the only real choice for any serious web application. It's the whole philosophy behind modern cloud computing, letting companies add capacity instantly for big events. But it introduces a brand new challenge. Okay, so now we've got this whole fleet of servers all ready to handle requests. But that creates a new problem, right? How do we decide which user goes to which server? They all have their own IP addresses, so we can't just point the DNS at all of them at once. We need some kind of digital traffic director. And here is the beautifully elegant solution. The DNS doesn't point to all those servers anymore. No, it points to just one address, the address of a load balancer. You can think of it as a traffic cop, standing right in front of all your servers. It intelligently routes all the incoming requests to the different servers, making sure no single one gets overwhelmed. And one of the simplest, most common ways to do this is called round robin. It's pretty much exactly what it sounds like. The load balancer sends the first request to server A, the second to server B, the third to server C, and then it just cycles right back around to A. It's a simple but really effective way to make sure the traffic is distributed perfectly. Now, as systems get bigger and more complex, they usually get broken down into smaller, specialized services. We call these microservices. So Amazon might have separate services for logins, shopping carts, and payments. An API gateway is like a smarter load balancer. It's a front door that looks at what you're asking for, like is this an orders request or a payments request, and it routes you to the specific fleet of servers that handles just that one task. All right, so we've built a system that can handle tons of users, but some things are just naturally slow, and we absolutely can't let that ruin the experience by making people wait around. Just think about it. You place an order, right? Sending that confirmation email might take a few seconds behind the scenes. Now, if the server makes you wait for that to finish before it tells you your order was a success, the whole website feels slow. It feels clunky. And those kinds of background tasks shouldn't block the application from responding to you right away. So the solution here is to work asynchronously. It's a key concept. When you place your order, the server instantly sends a success message back to your screen. At the very same moment, it just adds a little note, a send email task, to a message queue. Think of it like a to-do list for the servers. Then, a separate worker service is always checking this list, it picks up the task, and sends the email behind the scenes. You get a super fast response, and the important work still gets down.
Okay, our system is getting pretty robust and responsive. But to make it feel lightning fast for everyone, no matter where they are in the world, we need to add two final layers. And these are all about pure, unadulterated speed.
Let's go back to that popular product page. If 10,000 people want to see it in 1 hour, why on earth would we make the main database do the same work 10,000 times? It's just insanely inefficient. So caching creates this short-term memory. It stores a copy of that page in a super fast layer. The very first request might be a little slow, but the next 9,999 requests, they get served almost instantly from the cache.
So a CDN, that's a content delivery network, basically takes this idea of caching and just explodes it onto a global scale. What it does is it puts copies of all your heavy stuff, images, videos, files, on servers located all over the planet. So a user in India gets images from a server in Mumbai, not one in Virginia. This dramatically cuts down latency, the time it takes data to travel, making the website feel fast for everyone, everywhere.
Okay, let's put it all together now. Let's trace the entire journey of one single request. You type Amazon.com. The DNS finds the CDN. The CDN serves up all the cache stuff from a server near you. For anything else, it forwards the request to the API gateway, which sends it to the right load balancer, which picks a healthy server. That server does its work, maybe using a cache or a message queue, and then the response travels all the way back to you. It really is an incredible symphony of all this technology working together in perfect harmony.
So, we've solved for scale, we've solved for speed, but all these moving parts, all this complexity, it brings up a whole new world of challenges around reliability and what happens when things inevitably go wrong. And building a system that can not only detect when something fails, but can actually heal itself, well, that's the next big frontier. But that is a topic for another explainer.